Hello, welcome to MECH 2040 Solid Mechanics. I am Globas. In this tutorial, I'm going to introduce you stress and strain and their concepts. So the agenda today includes 1.1 direct stress, strain, and deformation. 1.2 shear stress and shear strain. 1.3 I will introduce you some examples about shear and shear strain. Also, I will introduce you what is the Poisson's ratio and what is the relationship between the Young's modulus and the shear modulus. In 1.5, we are going to study the sign convention of shear forces, while in 1.6, we are going to learn a little bit about stress-strain diagram of materials. So this concept will be introduced in MECH 2410, Engineering Materials 1. You will do a lab for that. So first, let me introduce you direct stress. So from the secondary school, we've already learned that when we apply a force on a surface, it will generate the pressure. So consider this region, and it has a distributed stress. The strength of the stress is shown here. Green means very small strength, while the red color means the strongest strength. So if we take a differential area, which is here, so the differential area is dA and the local pressure is P, then the differential force acting on the region will be dF. And similarly, as what we did in tutorial 0, to get the sum of the force, we do the integration of the pressure distribution with this. So this is the pressure distribution. We do the integration of the pressure distribution over the entire region to get the total force. But I believe such thing will not be used anywhere. Just give you some very simple introduction. And the local pressure for the non-evenly distributed pressure, like this. So you can see the stress is not evenly distributed. Then you can only say, okay, the pressure here is what? The pressure here is what? Or you may want to say, okay, the average pressure is what? We can say the pressure, the local pressure, that means the pressure of one point on this region, P, will become the limit of the very small area near this point. Differential force divided by the differential area. So those are very basic concepts about pressure. Now let's consider a uniform cross-section. So for example, now you have a bar. It has a rectangular cross-section. And for this rectangular bar, there is a cross-sectional area A, and its cross-section is uniform. You apply the load P on the two ends. So the behavior of the bar in the solid mechanics will be rather similar to the behavior of a spring. What does that mean? When you stretch a spring by using the load P, the spring will become longer, and when you compress the spring, then the spring will become shorter, right? So this is what we are dealing with actually. We consider the material as the linearly elastic. That means like the spring. So we know that for spring, when you apply the P force, then you will get F equals to minus Kx. Still remember that? So it is similar, it is quite similar in solid mechanics. Okay, so we consider there will be a constant that is linearly related to the distance and the force. So only thing is that we change the notation from F to P, and we will change the notation of the stress a little bit, because in this course we consider two kinds of stress. One is the direct stress, one is the shear stress, which is to be introduced to you later on. So for the direct stress, it is called sigma. Sigma is defined as the force acting on this area, and we assume it is uniformly distributed. So this is the distribution. Then the direct stress will be, of course, similar definition. The force divided by the area. And notice that it has the unit of Newton per meter square. So you know that the force has a unit of Newton, area has a unit of meter square, then the unit will be consequently Newton per meter square. And those formulas can be very similar to what we just introduced. So you know the force is the area integral of the pressure distribution. And very similar for a spring, when you have a tensile load P acting on the tip, it will become longer. If instead you have a compressive P, then the spring will become shorter. So rather similar to the spring, when you apply a compressive load, we treat this load to be negative, and the delta is a deformation of the material. So back to the solid mechanics, we have a bar. In case we have a compressive load P, then the bar will become slightly shorter, and there will be a deformation. So for the deformation, you know that it is relevant to the force, and in this course we define that in case you apply a compressive force, that means you will make the deformation negative. That means in case the deformation is negative, the bar is shortened. And similarly, in case you apply a tensile load P, then the bar will become slightly longer, and the delta will become positive because the bar has been elongated, and consequently we will treat this tensile load as positive. It is rather similar to what we have learned in statics and dynamics. So as you can see, when you apply a load P, there will be a deformation. Notice that the deformation can be either positive or negative, depends on your P. So in case your P is pointing back, then your beam will become shorter, then maybe this part will become shorter. And notice that, of course, the deformation is very often not that big, so it is just an enlarged view. So actually, in our daily life, the deformation of the material is very, very small, maybe. So we know that the normal stress is given by P divided by A. We will define some quantities in order to proceed. So we will define the axial strain. What is axial strain? It is called epsilon. So epsilon equals to delta divided by L naught, where L naught is the original length of the material under no load. When in case there is no load applied, the original length is L naught. So epsilon is just the amount of deformation divided by the original length L naught. And in case we assume this material is linearly elastic, there will be some quantity like K, right? Because we know F equals to minus Kx for springs, right? But for solid mechanics, instead of using K, we will use E. Okay, so we have a material property E, varies with materials. This property is called Young's modulus, so you might have heard it in Physics 1112. And now introduce the Hooke's law for axial stress and strain. So Hooke's law, you have heard it for a lot of time. For springs, it is F equals to minus Kx. But now we just try to use it to be something in the solid mechanics. It means that the normal stress, so the unit of stress is Newton per meter square, okay? So it equals to Young's modulus times epsilon. So notice that, what is the unit of epsilon? Epsilon equals to delta divided by L0. So the unit of delta is meter, is the length, right? L naught, the unit is also length. Length divided by length means no unit, means it is 1. So the unit of Young's modulus will be Newton per meter square as well. So Hooke's law of axial stress and strain means that the axial stress equals to the strain times the Young's modulus. Notice that the larger strain means larger deformation. Consider the definition of the strain. The larger stress developed in the cross-section of the material. Harder material has harder Young's modulus. So just now we have already discussed the units of Young's modulus. So to emphasize, the unit of Young's modulus is just the same to that of the pressure or the stress. And also, by using all those three formulas, we can derive the deformation of the material under load P. So delta, we will rewrite this one to be delta equals to epsilon L naught. And we substitute the Hooke's law and make the epsilon to be the subject. Then it will become sigma divided by E times L naught. And at the same time, we keep those two here, okay? And we write sigma equals to P divided by A here. And eventually, you can have this formula. So it is the deformation of a linearly elastic material. So in case the original length, the L naught is L, then the formula will become delta equals to PL divided by EA. Well, how can you remember this formula? I believe all of you have taken ALPA exam, right? So it is just ELPA ALPA, English Language Proficiency Assessment, right? So delta equals to ALPA. Okay, remember PL divided by EA. ALPA. No ALPA. ALPA, okay? ELPA ALPA. I don't want ALPA, right? So all those formulas are only applicable for ball with uniform cross-section. As an important reminder, P can be either positive or negative. That means the deformation can be either positive or negative. Okay, so the beam can be elongated or shortened, depends on the loading conditions. So how about non-uniform cross-sections? So we know in this world we are not always dealing with wonderful conditions. We need to deal with some real situations. Let's see this beautiful curve. So let x-axis pointing into the paper. By the right-hand rule, still remember that when we construct the 3D space coordinate system, we use the right-hand rule. So x is pointing into the paper, y is pointing upward. Then the z-axis will be pointing rightward, right? Now, at least we know that, okay, it is a non-uniform bar. That means the cross-sectional area of this bar is no longer a constant. It will become a function of z. So A is AZ. Under external load P, for every position of this beam, the axial strain will be different. So still remember that in case we have the load P, that means everywhere in this beam will exert the load P, right? For any place, everywhere in the beam, you will have the direct force P acting on this variable area AZ. We know that epsilon equals to sigma divided by E, which equals to P divided by AE. But now, AZ is a variable instead of constant. So just now, in the uniform bar case, we know that the strain is constant everywhere. But now, A is a function of Z. So as a result, the axial strain, epsilon, at every place of this bar are varying, they are changing along the z-axis. Let's give this uniform bar an assumption, which is very often. That is, we set E to be constant everywhere. Then P, E are constant. Then we just consider the change of the area. At some position Z, the stress at this position will become P divided by A of Z. Then you can find the local strain. Epsilon Z equals to sigma Z divided by E. Then you make the substitution. We know that from previous case that delta equals to epsilon L, right? But we consider a slice, a thin sheet of material with the variable sectional area, which has the thickness dz, very small thickness. Then for this differential segment, the deformation will become delta equal to epsilon times dz. dz is the differential length of this slice. So for this slice, it is very thin, okay? So we assume on this very thin slice, the epsilon, the strain, will be the same over this very small slice. And then we just use this relationship to find d delta equals to epsilon of z times dz. Finally, we combine all those relationships, then we can find the differential change of length, which is P times dz divided by EA of z. And finally, you take the integral. Then you will get this result. A remark is that in the textbook, they use X instead of Z because in this course we only consider the 1D loading. What does that mean? That means maybe your loading is like this, but it is 1D. In the reality, not only 1D, we still have the loading, which is about x-axis, which is pointing to the x-axis, but you cannot see it here. So in this course, we only consider 1D loading, but I still recommend you to use Z, because in advanced solid mechanics course, we will use Z instead of X, because X is often used to calculate the sectional properties. I will introduce that to you later. However, one thing you have to know is that in the lab or in the problems we are going to solve in this course, we will often see a term called strain gauge. What is strain gauge? Strain gauge is a sensor to measure the local strain of a piece of material. So for example, if you place a strain gauge here and you place a strain gauge here, so there are two sensors. Those two sensors are detecting the local strain on that particular point, and they will give you a reading. So which one do you think the reading will be bigger? The answer is this one will become bigger. This one is bigger. Recall the formula of the strain. The strain is given by the local stress divided by the Young's modulus, where the local stress is given by the applied load divided by the local cross-sectional area. So of course here the cross-sectional area is much more smaller, so the local strain here will be very large in comparison to that of here. Let's do an example. So now we are going to find the deformation of this concentric wooden cylinders. There are three loads applying on it. Those two pieces are sticked together. They are one piece. They are not separated, okay? So in order to do this, we need to consider the free body diagram of each of them. So we need to identify the external load exerted on each segment. So we call it segment 1. This is segment 2. For segment 1, as you can see, there is a PA of 20 kN transferred here. And also, since those two pieces are sticked together, if PC is exerted on segment 2, then the segment 2 will also pull this surface to the right hand side. Therefore, we conclude that there are 3 forces in total acting on this surface, and the resultant will become tensile 20 kilonewtons. This beam is clamped to this wall. And in order to remain this segment static, there will be a 20 kilonewton reaction given by the wall. Therefore, this segment is in static state and it is in tensile stress of 20 kilonewtons. What we can do is to use the alpha formula. Delta equals to P1 L1 divided by E1 A1. While the Young's modulus is the same for both of them, while the applied load is what we know. Remember, try to convert everything into the SI units first to get rid of confusion. Then you will get the result of 0.252 millimeters, which is very small in comparison to the original length. How about segment 2? PC is 25, PB is 15, PA is 20. But it is not the end of the story, because you can see it is obviously not in static. But there will be P1 equals to 20 kilonewton applied here, because as a reminder, we know that there is a 20 kilonewton P1 applied here, applied at the segment 1. Therefore, there will be a 20 kilonewton reaction pointing leftward, acting on segment 2. Consequently, the resultant of the system will become 20 kilonewton in compressive form. Therefore, we can calculate the deformation by using the alpha, PL divided by EA. Notice that in the compressive form, the P, the applied load, will become negative. The deformation, even if it is compressive, is much more smaller than that of segment 1. Therefore, what we can do is to add them up. Add the deformation of the whole piece together, which is delta 1 plus delta 2. Notice that we will account the symbol as well, because for segment 1 it is elongated, while for segment 2 it is shortened. The total deformation will be 0.236 millimeters. You can try this problem yourself after viewing this video. Next is talking about non-uniform bars. So the circular bar, this problem is a little bit complicated, so I will use numerical method. So I used Wolfram Alpha to solve this problem. So it is just give you an impression about how can you deal with the variable cross-sectional problems. For this circular bar, the radius is given by 0.3 sine z plus 0.5, and there is a compressive load P equals to 100 Newton. Estimate the minimum and maximum absolute reading. Absolute reading means that no matter whether it is positive or negative, we take the absolute value. And the total deformation of the bar. So in order to solve this problem, we observe that the maximum absolute local strain occurs at the location of minimum cross-sectional area. Recall that Rz equals to 0.3 sine z plus 0.5. The cross-section is a circular region. Therefore, we conclude that the minimum cross-sectional area occurs at the minimum radius. In order to make the radius minimized, we take sine z equals to minus 1. Therefore, R equals to 0.2. Consequently, we can find the minimum cross-sectional area. Next, we can use the stress equation, which is applied load divided by the area, to calculate the maximum stress in the structure, which is compressive 7.96 milliPascal. Therefore, the maximum absolute strain is by using the maximum stress divided by the Young's modulus, then take the absolute value, then you will get the answer, which is 7.96 times 10 to the power minus 4. By similar manner, in order to calculate the minimum stress, we will find the maximum cross-sectional area. Recall that R set equals to 0.3 sine set plus 0.5. Therefore, if we take sine set equals to 1, then the maximum radius will be 0.8. Therefore, the maximum cross-sectional area will become pi times 0.8 squared equals to 0.64 pi cm squared. Notice that the minimum stress, still it is compressive, it is negative, but we can observe there is a change in cross-sectional area, right? So the minimum stress is compressive 0.497 milliPascal. Consequently, the minimum absolute strain is given by the stress divided by the Young's modulus, and then we take the absolute value. Then the result will become 4.97 times 10 to the power minus 5. Next, we want to find the total deformation of this circular bar with the variable cross-sectional area. If you still remember, delta equals to the integral from 0 to L P dz E A z, where P, E are both known. For A z, we know that it is a function with dependent variable z. Therefore, we can write the cross-sectional area in terms of z, so area is pi r squared, and r is given by this formula. Therefore, A z can be written in this form. After we identify A z and we know P and E, then we just take them out and substitute A z into the expression. After that, we will eliminate the units. We make everything into the SI units in order to get rid of being confused. Eventually, we will get an integral like this. However, since this piece of integral is very difficult to be solved, the only way you can do it is to use some online widgets such as Wolfram Alpha. So I used Wolfram Alpha to solve it, and eventually the result is minus 0.0189 millimeters. That means the deformation is negative and the bar is become shortened. It is shortened by the external load by 0.0189 millimeters. Finally, check that the epsilon, the average strain, is bounded by the minimum and maximum value. That indicates that our answer is reasonable. Next, let's talk about shear stress and shear strain. When talking about shear, instead of using P, we use V to denote the shear force. Notice that in the previous section, we talked about direct stress. That means P is normal to the surface where the force is exerted, right? Those two forces are perpendicular to the applied load P. But this time, since we are talking about shear stress and shear force, it is different from the direct stress. As you can see here, if we have a prismatic block with its bottom fixed, then if you apply the shear load V, the V is parallel to the surface concerned. Then it will generate a shear strain, as shown here. So recall that the largest difference between direct stress and shear stress is that for direct stress, your force is perpendicular to the applied surface. For shear, your force pairs are parallel to the surface exerted. So in this case, when you have a shear force V acting on this surface, then consequently, this fixed surface will give a reaction V in order to cancel it out. When you apply the shear force V onto a surface, then there will be shear stress on it. However, the same to the direct stress, shear stress on the surface is very often uneven. Therefore, we can compute the average shear stress, which is given by tau equals to V divided by A. This definition is very similar to what we just discussed, which is sigma equals to P divided by A. talk about the Hooke's laws in strain. So just now in direct stress part, we know that the Hooke's law is given by sigma equals to E epsilon. This is Hooke's law in direct stress. Now, since we are talking about the shear stress, it has another Hooke's law, which is concerning in the shear stress and the shear strain. Assume your shear force is evenly distributed over the entire region, so that you can have a uniformly distributed shear stress. The Hooke's law in shear stress and strain is given by tau equals to G gamma. Tau is the shear stress, G is the shear modulus, gamma is the shear strain. Just now we introduced that sigma is the direct stress, E is the Young's modulus, where epsilon is the axial strain. Notice that although we have E and G as constant, but in case of shear strain and the axial strain, their constants are very often unequal. That means G is very often unequal to E for some special cases. And let's have a look of this 2D block. Under the shear force V, the shear force caused the deformation of this shape. And here is D, here is L. We know that shear strain is actually an angle. So unlike axial strain is non-dimensionalized quantity, which is the ratio between the deformation and the original length. Here, shear strain is also a non-dimensionalized quantity, which is an angle with the unit radian. However, since we know that in radian, tangent gamma is approximately equal to gamma in case the shear strain is small. What is tangent gamma? Well, tangent gamma is significant. It is D divided by L, according to the geometry here. Therefore, in case the shear strain is very small, we can write gamma equals to D divided by L. In our textbook, there are two examples of shear and shear strain. Let's go through it. As you can see, a bolt is installed on an I-shaped beam, and there is a load P pulling this bolt outward. So now let's concentrate to the bolt and forget about this I-shaped structure. So for this bolt, the load P is uniformly distributed on the right half of it. While in order to keep it equilibrium on the left half of it, there must be a P pointing downward. As a result, the upward and the downward force pair will form the shear stress on the surface MN. So how can we calculate the shear stress? Shear stress is like a pair of forces. So now it is rather similar. At the cross-section MN, there is a pair of shear stress P exerted on it. Therefore, we can calculate at the surface MN what is the average shear stress. So the average shear stress is given by the force divided by the cross-sectional area. Since it is a circular bolt, the area is given by 1/4 of pi d squared. Therefore, it equals to 4p divided by pi d squared. The textbook also gave us a double shear example. Consider a bolt installed here. It is under a double shear with P exerted in the middle, with 1/2 of P exerted on the two ends, respectively. If we only consider the section in the middle, MNPQ, there will be shear stress V acting on MN and the shear stress V acting on PQ. However, what is the magnitude of V? In the middle, it is P. That means 2V equals to P. Then V equals to P divided by 2. So what is the average shear stress acting on surfaces MN and PQ? It is given by shear force divided by A, and the shear force is 1/2 of the applied load, which is P divided by 2, where the area is similar, which is 1/4 pi d squared. To further simplify this expression, it gives you 2p divided by pi d squared. Let's talk a little bit more about a bolt. When the bolt is subjected to a compressive load P, like this, then there will be a pair of direct force acting on its cylindrical surface. Then, for the cylindrical surface, there would be a pressure distribution, depends on the geometry, and typically it will be like this. However, in the engineering application, we are not interested to the exact distribution of the stress. Instead, we try to define a stress called the bearing stress. The cylindrical surface, which is the contact surface, or the bearing surface, will have a bearing stress defined as sigma B equals to P divided by A, where P is the external load. But here, the area is not the cross-section. No, it is not. The area is a rectangular region, which is here. So the area is given by T times D, which is a rectangular region, lies in the middle of the cylinder. The bearing stress means the average stress acting on the bolt. Some of you might have already attended the industrial training at Polytechnic University in this winter. In the sheet metal unit, you might have experienced the operation of shearing machine. For those who didn't attend the industrial training, you might want to get some understanding about what a shearing machine is. Basically, it is a machine that cuts a piece of sheet metal. So let's have a look.
Learning through the camera. You recording?
Yeah.
You got this?
I got it.
Okay. My other mark is right on. I'm at 6 inches. I want to make sure that I'm square here. Shear that strip and let it drop on the backside. We have a tray back here that will catch it. So now I've got a 6-inch strip by 20 something.
So as you can see, the shearing machine successfully cut a piece of metal from the sheet metal given. The question is that, as what we have learned from the industrial training, the cutting edge of the material is extremely sharp. So what is the reason? The reason is that when a piece of material is cut, for example, it is cut here, then the material near the cutting surface will be deformed. It is like this. So the material is originally like this. However, when it is cut, the material will deform so that a very sharp edge will be generated. Another example is the scissors. So when you are cutting a piece of material by using your scissors, you are actually applying the shear force on the surface that you are going to cut. So this is the surface you are going to cut, and those two are the blades of your scissors. Then the average shear force will become your applied load divided by the cross-sectional area. If you want to get some more understanding of shear force, you can go to the website in the reference. Let's talk about an example which occurred in the lecture notes last year. Consider the following system. AB is a rectangular bar, while BC is a circular bar. All the 3 pins located here have circular cross sections. We are going to find several things. One is the average normal stress in the beams AB and BC, so we are interested to the average normal stress in those 2 beams. Also, we are going to find the maximum bearing stress in the 3 pins. Besides, we are going to find the shear stresses tau in the 3 pins. So basically, the stress of this problem is put at those pins instead of the whole structure. Firstly, let's consider a simplified schema to find the loading on each member. The structure is simplified like this. And for point B, we can draw the free body diagram for this joint. At this point, consider the force equilibrium triangle, which has already been taught in static and dynamics course. It looks like this, and we can find the magnitude of force in AB and BC by using this triangle. By this geometry, we know that tangent theta equals to 600 divided by 800, which equals to 3 over 4. Consequently, we can find sine theta and cosine theta are 0.6 and 0.8 respectively. Therefore, by using the trigonometry, we can find the magnitude of force in AB and BC. In AB, it is Q divided by tangent theta equals to 40 kilonewtons, while for BC, the magnitude is Q divided by sine theta equals to 50 kilonewtons. Notice that BC is a tensile load, while AB is a compressive load. So we convert the results into the symbol carrying quantities. For AB, since it is compressive, then it is negative sign, which is negative 40 kilonewtons. For member BC, it is in tensile load, so it is positive 50 kilonewtons. Now let's consider the cross-sectional areas for members AB and BC. Recall that AB is of rectangular shape and the BC is a circular bar. For AB, it is rectangular. It has the dimension 50 times 30. Therefore, its cross-sectional area is 1500. Besides, for the cross-sectional area of bar BC, since it is circular, and we know that its diameter is 20 millimeters, then the cross-sectional area is 100 pi millimeter squared. Therefore, we can calculate the direct stress by using the force divided by area. Sigma AB is minus 40 kilonewtons divided by 1500 millimeters squared, which is negative 26.7 million Pascal. It is a compressive stress. By a similar manner, you can find the stress in member BC, which is 159.2 million Pascal. We will now combine problem B and C together because they are rather related to the bolts. Consider each of the pins. For pin at A, it is under double shear. Therefore, we know that 2P equals to 2V equals to 40 kilonewtons. Notice that the shear load P located here is just the V, the shear load. So the shear force for each side is 20 kilonewtons. Therefore, we can find the average shear stress by using the shear force divided by the area. Notice that it is circular cross-section. The result will be 40.7 million Pascal. For this pin, there are 3 direct forces acting on the cylindrical surface. For each of them, they generate different bearing stress on their respective contact surface. The maximum bearing stress occurs in section DE. Notice that the D is 25 millimeters, while T is 30 millimeters. Therefore, the maximum bearing stress will be 40 kilonewtons divided by 30 times 25 equals to 53.3 million pascals. For pin C, it is subject to single shear. Notice that the bearing area of the 2 direct stress to the pin are the same. For the single shear, the shear force is just 50 kilonewtons. Therefore, P equals to V equals to 50 kilonewtons. Then the average shear stress is given by 50 divided by the cross-sectional area of the circular pin. Then the shear stress is given by 101.9 million pascals. For each of the contact surface of the 2 direct forces on this pin, the bearing areas are the same. The bearing stress are the same. The magnitude of the force is 50 kilonewtons, while its diameter is 25 millimeters. T is given by 20 millimeters. Therefore, its bearing stress is 100 million Pascal. For pin B, its shearing condition is a little bit complicated. As you can see, for pin B, it is subject to multiple shear. That means there are a lot of forces acting on this pin. Notice that FBC is the tensile load of BC. In this case, the maximum shear stress occurs at cross-sections G and H. You can find the maximum shear stress by finding the shear force in that cross-section. I leave you as an exercise. It should be easy to find it. You decomposite FBC into X and Y directions. Then it will cancel the 1/2 FAB and the 1/2 Q out. And it will have a net force on the surface G. And it is similar for H. Then you can use the Pythagoras theorem to find the net force on G and H. The result of the maximum shear stress will be 50.9 million pascals. Also, in this case, since there are direct forces acting on different sections of the bearing surface, the largest load is 50 kilonewton, and it is exerted in a relatively small region. The maximum bearing stress is therefore 50 kilonewtons divided by 20 times 25. The result will be 100 million Pascal. Next, I'm going to introduce you the Poisson's ratio. As a direct stress applied, it will be elongated or be shortened. However, as we know, we have conservation of mass. That means once a material is being stretched or shortened, then there will be strain in the lateral direction, which is the lateral strain. So we'll denote it as epsilon prime. Notice that when the axial strain is positive, that means the beam is being stretched, being elongated. That means the lateral strain will become negative, because once you stretch a piece of material, that means in the lateral direction its dimension must be reduced. And similarly, when you compress this piece of material, the lateral strain will be positive, because when you compress this material, then your axial strain will be negative. That means the dimension of your lateral direction will become larger. Therefore, the lateral strain will be positive. So you can draw a conclusion that either axial strain or lateral strain will be positive. Exactly one of them is positive. The other one must be negative. So the Poisson's ratio is defined as mu equals to the lateral strain divided by the axial strain equals to minus of epsilon prime divided by epsilon. Notice that Poisson's ratio can be either positive or negative, but in fact we try to assume that this material has a positive Poisson's ratio. In later chapter, you will learn the relationship between the shear modulus and the Young's modulus. So as we described before, the shear modulus is very often different from the Young's modulus, but they have the relationship G equals to E divided by 2 of 1 plus nu. For axial stress, tensile is positive and compressive is negative, right? This is for axial stress. But for shear stress, as you know, it is something like change of shape. There is a shear force. So you know that the shear force, if we observe in this way, they are in opposite direction, but we cannot determine what is positive or negative. So now I will introduce you what is the sign convention of shear forces. First of all, let's try to understand what is positive and negative surfaces. Consider x, y, and z axis shown here, and those three faces are facing outward. For those three surfaces facing outward, it is called the positive x surface because it is facing outward, and x-axis is the outward normal to the surface. This is called positive y surface because it is pointing outward, and the positive y-axis is the outward normal to this surface. The surface here is called the positive z surface because it is pointing outward, and the positive z-axis is its outward normal. Similarly, this surface, which is not facing to us, is called the negative x surface because negative x-axis is its outward normal. For negative y surface, negative y direction is its outward normal. Similarly, for negative z surface, negative x direction is its outward normal. Let's play again. This is positive x surface, positive y surface, positive z surface. So those surfaces facing to us, and the axis is the outward normal of it, then those surfaces are positive. Then negative x surface. So you can see negative surface and the positive surface, they are opposite, parallel, okay? So this is positive x. And the negative y surface and the negative z surface. After we're talking about the positivity or negativity of the surface, let's talk about the shear force. For the shear force, we still have to talk about its direction. So one important thing I have to mention is that even though, say, you apply a force here, it is upward, then it is not enough to say, okay, it is positive force. Or if you say, okay, if you draw a downward arrow and say, okay, it is a negative force, then still it is not enough to say that. How can we name those shear forces or shear stresses? What is positive shear forces? Positive shear forces means it is acting on positive surface and pointing to the positive direction of the xy set. For example, this is a positive surface. Your force is pointing to the positive z direction. Then I can say it is positive shear force acting on the y surface pointing to the positive z direction. And this is a positive shear force. Similarly, if you say I have a force like this, is it positive? The answer is yes, because it is acting on positive y surface pointing to positive x direction. Those are all positive forces. For example, tau yz, that means it is acting on positive y surface pointing to positive y axis. And tau yx means it is acting on y surface pointing to the positive x direction. Tau xz means it is acting on the positive x surface and pointing to the positive z direction. And the tau xy means it is acting on x surface pointing to the positive y direction. Tau zx means it is acting on the positive z surface pointing to positive x direction, while tau zy means it is acting on positive z surface and pointing to the positive y direction. For negative surfaces, it is quite similar. 6 possible shear stresses. Tau xy means it is acting on the negative x surface pointing to the negative y direction. Tau xz means acting on the negative x surface pointing to negative z direction, etc. As long as the symbol of the surface and your direction are the same, then your shear stress is positive. One problem is that, okay, you might want to ask, what is tau xx? The answer is no, there is no such thing acting on x surface pointing to x direction. Then what is that? Let me take positive y surface as an example. If a force is acting on the positive y surface pointing to positive y direction, can we still call it shear stress? No. The reason is that here, this force is normal to the surface. That means now it is the direct stress instead of shear stress. So there is nothing like tau xx. No, it is sigma xx. There is no tau xx, tau yy, tau zz. We only have direct stress instead of shear stress. And similarly for the negative surfaces. So still, for the direct stress pointing outward means positive. For the sign convention in 2D case, this is positive. Why? Because the force is pointing to the positive x direction. This surface is defined as positive y surface. That means the shear force direction and the surface symbol are the same. So this is pointing to the positive direction and this is positive surface. Then this shear force should be positive. Similarly, it is pointing to the negative direction. It is negative surface. Then it is also positive. Therefore, we can say that this pair of shear stress are positive, or this pair of shear force are positive. And similarly, you can compare those two cases. You can immediately see what is positive or negative. So you can say, like in 2D case, if you shear like this, you lean rightward, then it will be positive. and originally you are like this, and you shear like this, then it will become negative shear, and the shear force will become negative as well. Finally, this is the last topic of this tutorial. All our discussion just now is limited to some theoretical results, but what are the real materials look like? I will play a little bit to you.
This is the test piece.
So,
it has a cylindrical test region with an original They help to visualize and measure the plastic behavior of the specimen.
This specimen will be placed
using a hand control
in this tensile test machine, and this machine will stretch the material so that it is elongated, and after that a plot will be generated.
Elongated with a standardized speed. The force that the test piece opposes, force F, is being plotted upwards on the vertical axis. In this area, the end of the elongation occurs. The material opposes an increasing force against the imposed elongation, its strain shape.
When the applied load P is large enough at the both ends of the material, then the material will gradually elongate it and then fracture eventually. So actually from this video we cannot experience how loud it is when it is fractured. When you do this lab in Mechan 2410, Engineering Materials 1, you will experience how loud it is when the specimen is broken. Okay, so this is the typical engineering stress strain diagram, and our discussion till now is just limited to the linear region. So we assume the epsilon is very small. Okay, so what if our material are stretched like spring, like something else? The answer is that beyond this proportional limit, you can no longer use the Hooke's law, because the material stress and the strain relationship is no longer linear. It's like this, a curve you can see. The proportional limit is the largest normal stress that remains Hooke's law valid. So when the stress is below this point, you can still use Hooke's law to calculate your structure, but beyond this point you can no longer do that. The Hooke's law will become invalid. Okay, yield stress is the stress that before the permanent deformation occurs. That means when using the tensile test machine, you will have the specimen. When the applied load is so large that it is beyond the yield stress, then after you remove the load, the specimen will not recover to the original shape. That means the stress is large enough, and when you continue stretch it, the stress even is not changing, but the length can change a lot, and it will never recover. When the stress goes beyond this point, the slope here becomes very small. During this period, even though the stress all the way is not changing, but the specimen is still become longer under this nearly constant stress. And after a period of deformation, when the material is long enough, okay, here the strain is much more larger than that in the linear region, right? So in case the material is long enough, then it will undergo the strain hardening process. What does that mean? Strain hardening means that the stress required to further stretch the material will become even larger until it reaches the ultimate stress. It is hardening the material. Hardening means that the stress is going up, okay, with the strain increases. So ultimate stress is the maximum stress before the fracture. So it is the peak of its entire life, and after this peak, it will become old and then die. After the plastic region, it undergoes strain hardening. It will further strengthen the material. The stress required to deform this material is increased, but one downfall is that in case you go beyond this region, then necking will happen. After you arrive at the ultimate stress, the stress will keep going down until it boom, dies, okay? And in this process, the necking of material will occur. So what is necking? Necking is like this. You apply your stress and it goes up, then it goes plastic deformation until it reaches the ultimate stress. Then the stress goes down and the neck is developing. Observe it. There is no neck, but there is neck developed as the stress increases. Because of the necking, the material becomes very weak in the middle. The material becomes weak and eventually it is fractured. You will learn more about the fracture in engineering materials course. This figure is come from the textbook of the material science and engineering, which is the textbook of 2410. One special case of stress-strain diagram is some of them that has no significant yield stress characteristic. Just now we discussed that for the typical material stress-strain diagram, when yield happens, it will be like this. After the proportional limit, there will be yield stress. Then there will be a sharp drop in the pressure, right? Then there might be a period of plastic deformation. However, as you can see, for aluminum alloys, it does not have the characteristic of the yield stress. From the stress-strain diagram, it is not easy to find what is the yield stress of it. In order to find it, we will adopt the 0.2 offset method to estimate it. So how can we estimate it? Still remember that we have the linear region. Then we plot the straight line of this linear region. Then we shift this straight line rightward by 0.002, that is 0.2%, along the epsilon axis. Then you will get another straight line after removing the linear region of it. And as you can see, this line intersects with the stress-strain diagram at point A. Therefore, we conclude that at this point A, the yield stress is achieved. Finally, let's do a quick summary of all about this tutorial. So in 1.1, we talked about the change of length of uniform bar and the non-uniform bars. For uniform bar, still remember it is alpha. For non-uniform bar, it is just like you rewrite this formula into the integral form. We also discussed the shear stress and the shear strain. The shear stress is given by tau equals to V divided by A. V is the shear force and the tau is the shear stress. A is the cross-sectional area. Notice that it is a kind of average. Also, we learned about Hooke's law in shear, which is given by tau equals to G times gamma, where gamma is the shear strain and G is the shear modulus. We also talked about the bearing stress on a boat The bearing stress is given by P divided by TD, where TD is not the area of the cylindrical surface. It is a rectangular surface, lies in the middle of the cylinder. Also, we discussed about the Poisson's ratio nu. Nu equals to minus of literal strain divided by the axial strain. We also discussed the relationship between E and G. So the shear modulus is given by E divided by 2 of 1 plus nu. Besides, we also discussed in detail about the sign convention of shear forces. In short, symbol of force is the same to that of surface, means that the shear force is positive. In another word, if the symbol of force is different from that of surface, then the shear force is negative. And those two are the 2D case of sign convention of the shear strain. For the negative shear strain, there will be negative shear force. Similarly, for positive shear strain, there will be positive shear force. Besides, we also discussed about the stress-strain diagram and some of their terminologies. We also discussed some special case, how to find the yield stress of materials like aluminum alloy. The answer is that we can try the 0.2% offset method to find the yield stress. This is all for this tutorial. Thanks for watching. You can find the table of content under the description of this video, as well as the handouts of this tutorial. Hope you like it. See you in the next video.